proud for the people who've been supporting me. That's definitely something that's next on my list.
Unit 6, it's got to do with error, accuracy, and uncertainty. It's got to do with when we take measurements. You must realize, and I've said this to you already, when we measure something, what is the limit of accuracy on that instrument you are using? The smallest scale division. If it's a ruler that's been calibrated in millimeter, then millimeter has a certain amount of inaccuracy on it. Okay, now, the types of errors that we get when we take readings. Now remember, for you to use a ruler is fairly simple. But to use it correctly, you must know things like, be careful of the error of parallax. When you take a reading, your eye must be directly above the measurement. You can't look at it at an angle. Do you follow me? Okay, because all of these things cause errors. Okay, so, an absolute error is the one that is determined by the limitation of the instrument in the first place. In other words, your ruler is calibrated in millimeter, so you can't go more accurate than a millimeter. And then the next part, and the method of measuring. If you use that ruler incorrectly, you're not going to have a proper answer. All right. So, an absolute error is determined by the limitation of the instrument in the first place, and in the second place, how you work with that instrument. If you measure with a ruler, and the measurement, the ruler is calibrated in millimeter, remember that there is always an error of plus half a millimeter and minus half a millimeter. In other words, the millimeter reading you got actually implies it lies between two ends of plus and minus half a millimeter. Okay. There's therefore a range of possible values. Now, the next type of error is a relative error. Now, we express this error as a ratio or percentage, relative ratio or percentage. And very simply, if you take your ruler and you measure the width of your book, you can tell me, let's say it is 250 millimeters. If I say to you, take your rubber and measure the width of your rubber, you will tell me maybe it is 15 millimeters. Are you with me? Now, the percentage error on the rubber is going to be quite large. You follow me? Because being out 1 millimeter on 15 millimeters is quite a large error. But being out 1 millimeter on 400 millimeters, it's so small, it's actually negligibly small. Do you understand? And that is what they mean by a relative error. An error of 1 centimeter on a measurement of 2 centimeters will be very significant. It's a 50% error. Okay? But an error of 1 centimeter on a measurement maybe of 10 meters, all right, is fairly insignificant. You follow me? All right. So, we say a relative error can be calculated as the absolute error. In other words, the reading that you've taken that is limited by the instrument and your method of using. All right? You take the absolute error, and you divide it by a calculated value times 100 to convert to percentage. Systematic or determinate errors, a source of systematic errors, can be determined easily. You can find the source of the error, okay? Because it's easily notable, so it can easily be corrected. For example, if I have a spring balance, and I did not zero my scale on my spring balance, and I added a 10 Newton weight to it, my reading is 10.2 Newton. I add another 10 Newton, I will get 20.2 Newton. So I know where the error is. Oh, I didn't zero the scale. Okay, we can subtract it from our reading. Okay, so that would be a systematic or determinate error. We can determine where the error was, and we can correct it. Random or indeterminate errors are slightly more difficult to find, because we don't know what we did wrong. Okay, and it can be, for example, a reading that is taken incorrectly. Okay, but if you take the reading incorrectly, consequently through your practical, you should also be able to get a result from it. But if you take a reading incorrectly now, and your next reading you read correctly, and the one after that is correct, and the one after that is incorrect, it's going to be very difficult to get a decent set of readings. Okay, readings that are constantly done incorrectly, okay, will cause the result to be precise but not accurate. And I'll come back to precision and accuracy in a moment. Random errors can be eliminated by experience and by repeating the reading and taking an average. Remember when we said we need to make a test fair? To make a test fair, one of the things we must do is take an average. Because the more readings you try and take as good as possible, the more accurate your answer becomes. Okay, and it will eliminate maybe one error where you took one reading wrong. It cancels out that error. Okay. Let's get this here. And there. Let me just lock it in place. Okay, accuracy. The accuracy is limited by the scale division on the instrument. You can never be more accurate than the instrument. The higher the number of significant figures used, the more accurate, the higher the accuracy. All right. So, if I want to measure the diameter of a pipe for a precision engineering, if I need to make a fitting for it, I will use a specialized tool, not just a ruler. Okay, and we get specialized tools that have got a finer scale division to make it more accurate, and we will have a look at them in a while. Okay, done. A ruler calibrated in centimeters will be less accurate than one calibrated in millimeters. I mean, that's logical, no? All right. Repeating measurements and calculating an average will also improve accuracy. Accurate values lie close to the true value. Here I've got a bullseye. If I am trying to hit the bullseye of the target, that's the true value. If I am accurate, yeah, on this one, there, all my shots hit the bullseye. It hit the true value. It's as close as possible to the true value as it can get. If I am inaccurate, I'm inaccurate over here because my readings are far away from the true value. If I have a fairly high accuracy, but some of my readings are around about, then I can say I have high accuracy, but I wasn't very precise. I made errors on some of my readings. Okay, and over here we have low accuracy, low precision. The accuracy, we were supposed to hit the bull. Only one of my shots hit the bull. So 1 out of, how many have I there? 7. I'm not very accurate. Was I precise in my error? Nope, it's all over the place. So I probably made different errors taking readings. So here we have precision is the ability to get the same result from experimental data. Okay. Yes. Probably. Okay. So the same result when values lie close to the true value, they are precise and accurate. Remember, accurate lies close to the true value. When values are similar, but they lie far from the true value, there we go. Our accuracy is low, but our precision is high. And when values are spread out all over the show, we did not work accurately and we did not work precisely. Our answers are not accurate and they are not precise. Then we get something called an anomalous result. If you take a set of readings and you set it up in a table, and from the table you must go and draw a graph, and you find that as you plotted your points on the graph, there was one point that sort of didn't fit the pattern. Are you going to adjust your graph like that? No, never. Okay? You will draw a straight line through as many or as close to as many of the plotted points possible. Please use a ruler to draw a straight line. We will ignore the anomalous result. Here I have another graph. All our readings form a very nice pattern, except that one. Am I going to draw the graph as it is drawn here on the board? Nope. I am going to ignore the anomalous result and draw a straight line. You follow me? If you're busy with the experiment and you realize this reading does not fit the pattern, you can throw the reading out and redo that one. Okay. If you keep getting one that doesn't fit, then you ignore it and you carry on if you've got 10 others that do fit. You understand? All right. Anomalous results. And lastly, we've already done a little bit on uncertainty. Where is this one? Oh, goodness me, there. Let's just lock it. Lock in place. Okay. Uncertainty, people, we said every measurement has a certain amount of uncertainty. This is determined by the unit in which it's calibrated. You can never be more accurate than the instrument. So a ruler calibrated in millimeters means that the closest reading that you can get would be to the nearest millimeter. It also means that on that nearest millimeter, there is an error of 0.5 millimeter up and 0.5 millimeter down. Okay. If you have a bathroom scale at home, you will see on the scale somewhere, I think it's calibrated to be accurate to the nearest 100 grams. So if you get onto that scale and it says you have a mass of 55.6 kilograms, it is going to be, or 100 gram is going to be 55 point, let's say, 67 grams. So the accuracy, it's the 67, that's 7/100th of a gram, of a kilogram, is not accurate. You understand? There's 100 gram, so 50 gram up and 50 gram down from the reading on the bathroom scale. You follow me? Okay, so uncertainties in readings can come from the measuring instrument. It can come from the item or the object being measured. Sometimes it's very difficult to hold the object still. It doesn't want to stand still. It's a living thing that's bouncing around. Or you have to take the measurement in a very, very dark room and you don't have a good light on you to make the reading. Okay. Also, uncertainty can come from the person doing the reading. If I have to read millimeters without my glasses, I'm going to make an error. Okay. Uncertainties can be reduced by calibrating instruments correctly. Now, normally, when we buy a ruler, we don't worry much about the accuracy of the ruler because we usually use it to draw straight lines. But if I need to measure the diameter of a pipe, I'm going to buy a caliper or micrometer, which has a higher level of accuracy. Okay, so you need to choose the correct instrument as well. And then your data must be recorded accurately. Now that one sounds stupid, but when it starts getting tired, and your concentration sort of lags, then very often, instead of writing down a reading of 3.25, we go and write down a reading of 5.23. Do you understand? Okay, it's just human error. And it usually happens when you start getting tired or working under pressure, that something is upsetting you and you can't concentrate. Okay, so working with results and drawing conclusions, we can compare results with one another, usually by drawing graphs. Okay, then possible ways of preventing errors, repeat and take an average. Know how to operate the apparatus. If I give a millimeter ruler to a grade 1 learner and I say, okay, measure the width of the book in millimeters, are they going to do it correctly? Probably not. They'll probably take the centimeter reading and give that number that they get. Do you understand? You need to know how to work with the apparatus. Avoid the error of parallax. That's a very common error that we make when taking volume readings, mass readings, balance readings, etc. Many of the newer instruments have got a digital display, and that to a large extent avoids the error of parallax. Okay, because it's easier just to take the digital reading. Then record values correctly. I'm not going to say much more about that. And round off numbers correctly. You can't be more accurate than the instrument. Be careful when you convert units, converting kilogram to gram, multiplying with 1,000, converting cubic meters to cubic decimeters. You must know how to do that so that you don't make errors with that. Okay, that is the end of this whole topic at this point. Unit 6, error, accuracy, and uncertainty. And once again, it's very similar to what we have done in the chemistry class. What is an absolute error? Yes, due to the instrument. It limits us so that there is always an error on your reading. And the error would be to the closest unit, the smallest unit on your instrument. No. The finest division on your ruler has millimeters, so the accuracy is to the nearest millimeter. It means that even your reading, if it's given in millimeters, is going to be out by plus or minus half a millimeter up and half a millimeter down. Your answer lies somewhere in between. All right. A relative error. We said normally it's expressed as a ratio or a percentage. For example, the example we did this morning as well, an error of 1 centimeter on a 2 centimeter reading is major. It's a 50% error. But an error of 1 centimeter on 250 centimeters is almost nothing. Okay. It's not significant then if we have 1 centimeter on 10 meters. Relative error is the absolute error divided by the calculated value times 100 over 1. No, it's just a relative error. You can give it as a percentage or just as a value. Systematic or determinate errors, we said source of a systematic error. We can find it easily and we can correct it easily. All right. It's something that you've done wrong consequently throughout your, maybe you took the reading on the edge of the calibration instead of in the middle or, yeah. Okay. Random or indeterminate errors, we said, are more difficult to pinpoint. We don't really know where they lie. Sometimes we've just taken a reading incorrectly. Sometimes you just didn't concentrate and you made an error, all right? Random or indeterminate errors. Accuracy. The accuracy of your instrument is limited by its divisions that it's calibrated in, all right? You can never be more accurate than the instrument, because the calibration of the instrument, if it is in millimeters, you cannot be more accurate than that millimeter, because that millimeter already has an error on it. So I can't say 15,275 millimeters. That's totally absurd. All right, it's a ridiculous answer, because the millimeter 27 is already inaccurate. Okay. They say the higher the number of significant figures used to record a measurement and present calculated data, the higher the accuracy. But remember, it is limited by the instrument. You cannot be more accurate than the instrument. That's impossible. If I have my ruler calibrated not in millimeters, but in tenths of a millimeter. Okay. We can improve accuracy by repeating measurements and calculating an average. Usually in science we do a minimum of 3. The more repetitions, the more accurate it becomes. Accurate values lie very close to the true value. I'll come back to that term in a moment. Precision, to be precise. The ability to get the same result from experimental data. Then you are precise. When values lie close to the true value, they are precise and accurate. So does being precise and being accurate mean the same thing? No, it doesn't. All right. I'll show you here. I have a target, and I am shooting my bow and arrow into the target. All right. I want to hit the bullseye, dead center. We take how many shots? 1, 2, 3, 4, 5, 6 shots, and we see what they do. Can you see over here, all the shots landed all over the show. So I wasn't very accurate because I didn't hit the bull many times. And I wasn't very precise because my shots went all over the show. Yeah, exactly that. All right. Here, my accuracy wasn't good because I didn't hit the bull. Okay? But it was very precise because all my shots are concentrated here in one place. Right. Here we have high accuracy because they're almost all in the bull, but they're not grouped tightly together. So not very precise. And over here, high accuracy, high precision, high accuracy because I hit the bull, I was accurate, and all my readings are together, close together. All right. So they are precise. All right. Anomalous results. What's an anomalous result? One that doesn't fit the pattern. How do we treat anomalous results? We ignore them, all right? You can try and retake the reading. Sometimes it does solve that one. Sometimes it's not always possible to go back and retake the reading because you take your readings and then the next day you plot your graph. So maybe it's not possible to go back. All right. Is an anomalous result. And that one is an anomalous result. It does not fit the pattern. Ignore it. If I'm working out an average of these values, will I use that one? What do we do with anomalous results? You ignore it. Do we use it to work out the average? No, it's anomalous. You ignore it. No, you ignore an anomalous result. Okay? Don't let it confuse you. If you've identified it as being an anomalous result, we know it's incorrect for whatever reason. So you don't want to make your readings inaccurate by using it. No. Okay. You understand? Uncertainty. Every measurement that we take has a certain amount of uncertainty. Once again, if we use our ruler calibrated in millimeters, the uncertainty is a millimeter, half a millimeter up, half a millimeter down, or front or back. So a ruler calibrated in millimeter will mean that the closest reading that you can get would be to the nearest millimeter. You cannot be more accurate than the instrument, and that millimeter reading implies there is an error of half a millimeter on both sides of it. Okay, half a millimeter more and half a millimeter less. So your answer should actually lie within a range. It's just not always... when we write answers for measurements, it's not always, if I said, what's the width of your book, to go and tell me 241 to 42 millimeters. Between those two is the width of the book. You understand? You will say 241, implying there is an error on the last unit. Okay. So, the uncertainties come first and foremost from the measuring instrument. Then the object being measured, if it's standing still or if it's a very soft material with not a well-defined edge, there are certain factors that can make it difficult to measure things. And then the person doing the measurement, if he knows what he's doing, there should be smaller errors than if he doesn't know what he's doing. Okay? Uncertainties can be reduced by calibrating instruments correctly. For example, if I work with the balance in the chemistry lab and I want to measure a mass of a specific substance, I zero the balance before I put the substance on it. Accurate calculations. In other words, we work out averages with which we do our calculations, and we need to record the data accurately. Human error. No. When we work with the results, and we draw a conclusion, we will always compare results with one another by drawing graphs, because it's the easiest. If I'm working with how fast, what is your speed when you start running during the first 2 seconds of a race, everybody accelerates. The green graph is right, and the red graph is me. He accelerates much faster than what I do. Okay? We compare the two graphs with each other. This one has a steeper gradient than that one, which if we have, what is this, a speed time graph, then that would be his acceleration, the gradient. Okay? Possible ways of preventing errors. People, it's common sense. Why do I list them like this? One of the papers that you have to write exams on is a so-called alternative to practical. And they go and give you a practical all in words with pictures and everything, and then they go and ask you, what could you go and do to this practical to make it more accurate? So now you have to go and look which of these things would be able to fit onto that practical. Okay, what can we do? So it's just sort of, it's just general of common sense stuff. Okay, yeah. Repeat measurements and take the average. Know how to work the apparatus. It doesn't help you have to work with a burette and you can't take the reading on a burette. Or if you have to work with a thermometer and you don't know where to take the reading. For that matter, if you have to work with a measuring tape and you don't know how the reading works on a measuring tape. Because that is also a problem. Do you understand? Okay. Avoid the error of parallax. Record the values correctly. In other words, concentrate. But everybody gets tired somewhere. It's very easy to make a mistake like that, especially when you're doing a lot of them over a long period of time. Round off numbers correctly. And be careful when you convert units. For example, kilogram to gram, or meters to centimeters, or millimeters. Okay?
want to run away with it. Those at the bottom will fight to survive. There is so much to expect. It's as good as it gets. And there is no feeling like that feeling. A game of margins, a game of thrills.
Oh, it might just bounce kindly. Even better than that.
Live sport is back on GoTV. It doesn't get any better than catching all the action from La Liga, Serie A, the Premier League, and WWE as it happens. Take it all in. Get GoTV and subscribe for the ultimate live sport on Supersport with GoTV Max. GoTV. Live it, love it.
Accommodation is the ability of the eye to focus on distant and near objects, and I bring it in contact with the electroscope. What you must keep in mind is positive charge can't move. It is the negative charge that moves.
The first one, EF, is then going to be 0 minus negative 2 over 4 minus negative 4. Look at my signs. If you go wrong there, if you don't substitute in brackets, you're definitely going to get wrong answers.
Not into sports. That doesn't mean you don't like a good cheer. Or enjoy getting out your starting block.
It's delicious.
Thank you.
Just because you don't like sports doesn't mean you can't appreciate goals.
Keep going, keep going.
A good pair of boots. The importance of a change room or a silky swing.
Well, now it's a party.
You can still revel in different kinds of defenders,
Really?
attackers, drivers, and the occasional swimmer. You can still make a good catch. Push yourself to the limit. Celebrate a good delivery and work your way up the leaderboard.
So use it.
After all, you don't need to take to the field to get a good dose of entertainment. We've got everyone covered with the best movies, series, docus, and more. When it comes to DSTV, you always win.
When does the magic start?
It already started.
Share with us on #LearnOn1. Tell us what you're learning and where you're learning it from. Send us your name and town to the One Africa TV's WhatsApp on 081 200 6659 or send an SMS to 555. One Africa TV. It just gets better.
Question 8D. Okay, if the aircraft flies the same journey on another day at an average speed, where are we now? Let me just get this 8D. So it's over here somewhere. 10. 8A, okay, B, C, D. Okay, if the aircraft flies the same journey on another day at an average speed of 460 kilometers, how long will it take? Now, time is going to be, what's the formula? No, what's the formula? Is it distance divided by speed? Distance divided by speed. Now the distance that it traveled, we got that from the previous question, was how far? 473. Just hang on, just hang on. What was the distance? 735. Okay, and the speed is 460. People, because this is still the question that you ask, why can we use the ordinary formula here? Because it's the total distance divided by the total speed. Or the average speed at this stage. No. All right, because they've given us average speed. And the answer over here is 1.6. And that is going to be hours. Are you with me?
Yes.
All right. Number 9. A passenger jet lands at a speed of 80 meters per second. In other words, the initial velocity is 80 meters per second. After landing, it slows down at a constant rate and comes to rest. So V equals 0 after a time of 45 seconds. Calculate the deceleration. In other words, we are looking for the acceleration. Which formula? V minus U over T. Yes, V minus U over T is equal to acceleration. So, V is 0, U is 80, and the time is 45 seconds. So, minus 80 divided by 45 is equal to minus 1.7 meters per second squared. Is it on the dot? 7? 7, 8. Okay. 8. 2 places after the comma is better than 1. Yes. Okay. It's a deceleration. Huh?
Initial velocity is what you start with.
Mm-hmm.
So if it's something starts from rest, the initial velocity
Is 0, yeah.
But if it's like this, where you only have one speed, and then your
initial is 80, yeah. They tell us it comes to rest. So initial is 80, final is 0. No? Okay. Determine the minimum length of the runway. Displacement, ut plus half at squared. What is initial velocity? 80? Ne? Yeah. And what is the time? 45 seconds plus half of, we've got acceleration minus 1.78. And the time is 45 squared. So, what's the answer? 1797.75 meters. Yes, meters. Any questions there? Who used a different formula?
Okay, so you use the 45 twice because you use time twice.
Yes. Could we use this one? Yes. But then we have to make S the subject of the formula. So maybe you would make a mistake because it's slightly more difficult than just substituting into a formula and adding up, no? Okay, but this one would give you the exact same answer. Yes, we can. Okay, I'm going to add a page. So we will say V squared equals U squared plus 2AS. Now V squared was given to us as, what is V? V is equal to 0. U was equal to 80. Well, acceleration, we calculated that as minus 1.78, and we are looking for S. Are you with me? Okay? Yeah? So you can now either first substitute the values and simplify and then take out A, or you can first take out A. It doesn't really matter. It's sometimes easier if you put in the numbers first. So we will have 0 is equal to 80 squared plus 2A, and what is S? 2A minus 1.78 times S. All right? So now, what's it, 6400? So I'm taking this one across the equal to sign. So 80 times 80 is, 8 times 8 is 64, no? So 6400, but minus. Why minus? Over here it is. Yes, I take it across the equal to sign. And on this side, I am left with, what is 2 times 1.78? Thank you. S. Can you see? Now it's easier to solve for S. Because here I'm multiplying. Are you with me? So if I take it across, I have to divide. So I have minus 6400 divided by minus 3.56 is equal to S. What's the answer? Is it the same? Yes. All right. It doesn't matter which one we do. I just always try and keep it as simple as possible. Yes. Yes. Okay, that was this one we did extra, ne? All right, now, number 10. A car brakes suddenly from a speed of 8, here's a typo, meters per second, ne? All right, to a standstill. So what is initial velocity? Yes, 8. What is final velocity? 0, yes, to a standstill over a distance of 6 meters. What is the deceleration or the acceleration? Acceleration is going to be change in velocity over change in time. What's the change in velocity? Final minus initial divided by, oops, we don't have time, we have distance. Which one do I use? I can't use this one. Yeah. Yes. We will use V squared equals U squared plus 2AS. With me? And we are looking for A. So we are looking for that one. What is V squared? 0. What is U squared? It's 8 squared. Plus 2 times, what's the distance? 6 meters. And we are looking for A. So, if I take 8 times 8 across, it becomes minus 64. Are you with me? Yes. We're looking for A. So, minus 64. And here 2 times 6 is 12. So, if I divide by 12, I should get A. So, A is equal to 64 divided by 12, 5.3, and it's minus 5.3 meters per second squared. Why? It's deceleration, eh? Yeah, it's fine. You can, but 5.3 is also fine. It's not an issue. Okay, how long did it take to come to rest? Now we are looking for time. We've got initial velocity, we said, is equal to 8. Final velocity was 0. Distance was 6, and we worked out acceleration to be? What was our minus 5.333. Okay. minus 5.3 recurring. All right, so how long now we are looking for? Time. Which one am I going to use? Which one has time? ut plus half 80 squared. Or v equals u plus at. V equals u plus at. Are you with me? Okay. So what is v? 0. U is 8. Our acceleration is minus 5.3 recurring, and we are looking for time. So, minus 8 divided by minus 5.3 is equal to t. So that is equal to 8 divided by 5.3. 1 point. Is it 1.5? 1.5 seconds. Okay, 1 seconds. Good. It becomes minus, yes. And when you multiply and you take it across, it becomes divide. No. Okay, no, but that's good. It's just practice. It's fine. Okay. All right, number 11. A stone is thrown vertically upwards with an initial velocity of 20 meters per second. Assuming the acceleration due to gravity is 10, so gravitational acceleration is 10, determine how high we're looking for S. Which is the hidden quantity? Yes, what's final? 0. Yes. Final velocity would be 0, because if I throw something upwards, it's going to go up, but slower and slower and slower, and then it's going to start falling back. So for a split second, it will be 0, there where it turns. Okay, which formula are we going to use? Displacement is u. No, v squared equals u squared plus 2as. V squared equals u squared plus 2as. What is v squared? 0. What is u squared? Well, it's 20 times 20, so it is 400. Twice our acceleration is 10, and the distance is what we are looking for. So we end up with minus 400 divided by 20 is equal to S. So the answer is 20. Yeah, S is equal to 20 meters. What does it mean if it's plus or minus? It's just going to indicate direction. In this case, my answer is negative. So negative is upwards. You follow? Number 12. Yeah, well, in this case, it means it is moving away from you. It is minus. Yeah. What's a 5 meters? It's an S, sorry. Me writing ugly. Number 12, the graph below shows the speed time graph of a moving object. Describe the movement during the first 20 seconds. Well, a speed time graph, if the line has a gradient, what does it mean? Constant velocity or constant acceleration? Constant acceleration. So we can say the object starts from rest and accelerates constantly for 20 seconds to reach a speed of 10 meters per second. You can go one step further depending on the number of marks. What would the acceleration be? 10 over 20, which is 0.5 meters per second squared. Yeah. Yes, perfect. Yeah, perfect. Acceleration is the gradient, so it's change in y over change in x, so it's 10 over 20, 0.5. Yeah. Okay. Now, describe the movement for the next 70 seconds. Now, this is a little bit tricky because we're starting at 20, so the next 70 seconds will end at 90. Not so? That's 20, 40, 60, 70 seconds. So we have to end over here. So discuss the motion. Well, for the next 60 seconds, I will be traveling at constant speed of 10 meters per second, after which I will decelerate with a constant value. It is 70 seconds. What is the deceleration? We can work it out. It's the gradient of the line. Does it only have to be that gradient over there? No, you can work out the whole gradient. So it's change in y over change in x. It's going to be 10 over 40. Yes, you could have said something like that. It wouldn't be wrong.
The object moves at a constant speed
Mm-hmm.
of 10 meters per second and then decelerates.
And then decelerates constantly.
And then
Just for the next 60 seconds, it's constant velocity, and then for 10 seconds, it's going to decelerate constantly.
for 0.25.
At a rate of 0.25 meters per second squared. Although it's only 2 marks, so I think if you said constant velocity and then constant deceleration, it would be acceptable. It's 2 marks, no?
When they say like at the heading they say meters per second
Yeah.
negative 1. So can you just write that at every answer like
No.
0.25 meters per second negative 1?
No.
Why is it negative 1?
Because that's the unit for speed. It is either meters per second or meter per second.
Yeah, so you can write it like that at your answer as well.
That is if the answer is speed, yes?
Yes, if it is like this.
Yeah.
Zero.
Yeah. Yeah, then you can use the unit. They're both the same, yes? Yes, it will be minus 0.25. That's quite correct. It decelerates. Okay. You can either say it decelerates at a rate of 0.25 meters per second, or it accelerates at a rate of minus 0.25 seconds. It means the same. Okay, and then calculate the total distance covered by the object. How do we get distance? We need to work out the area under the graph. So how do we get the area? This one has nicely been divided up into rectangles and triangles. So that would be half base times height. That would be length times breadth. And that would be half base times height. So I will have half of 20 times 10 plus, what's that? 10 times 60, 10 times 60 plus half base times height, half of 40 times 10. And we add all that together and we will get 900 meters. Seems like you can do that at this point. No, it's not square meters. It's meters. If you have a meter per second and you multiply it with a second, you end up with a meter. No, a meter. No, it's not square. It's just a unit. All right. The next two. Is that the acceleration? Okay. Describe the motion. Yeah. What is the value for the motion in A? We have to calculate the acceleration, which we said is the gradient of that line. So it's change in Y over change in X. 10 divided by 20 is equal to 0.5. Let's just do it where or here. So it is 10 divided by 20 is equal to 0.5 meters per second squared. And you need to know it's the gradient. If you don't know it's the gradient, so it's 1 mark for knowing you need to calculate the gradient, 1 mark for working out what the values are, and then 1 mark for the answer. All right. And then the last part, the acceleration on the last part of that graph, we have to get the gradient of the line. So now we need the gradient of this line, which is going to be change in y over change in x. It's 10 divided by 40. And it's actually minus 10 divided by 40, not so? Yeah, so minus 10 over 40 will give me minus 0.25 meters per second squared. Any questions on that? You should be all right with that. I've written this in the wrong place now. Seriously, yeah. Okay. Was it in? No, it was in the right place. Okay. Yeah. I can just do undo. All right, now. Number 13, the graph below to answer the following questions. Now, I don't have a velocity time graph. What do I have? A distance or displacement time graph. Describe the motion. Well, traveling at constant, not acceleration. We have a displacement time graph. The gradient now gives me the speed or velocity. So traveling from rest at constant speed, no, not from rest, traveling at constant speed for 20 seconds. Or from the start. Yeah, with a constant speed. No? Okay. Covering a distance of 10 meters in 20 seconds. And then we carry on. What's happening over here? Yeah, we are standing still for the next 60 seconds. We have stopped. 20, 40, 60 seconds. Okay? And then what has happened? Moved in. No, it doesn't decelerate. It moves in the opposite direction because this was a positive speed, and if that's a negative speed, it means the opposite direction. So it will go backwards at a constant speed for the next 40 seconds. What is the maximum speed reached? Get that from the graph. The maximum speed is going to be the steepest gradient. Do you agree with me? Which gradient is steeper? That one. Okay, so what is the maximum speed? We have to get the gradient change in y over change in x. So it's 10 over 20, so it's 0.5 meters per second. No. Where did you get the distance? With 10 over 20, in this case it's going to give you probably the same, 10 divided by 20, yeah. But it's better to use the gradient. Okay. All right. That is the end of that worksheet. I think we will stop there.